Well, good morning, afternoon, or evening. I'm Professor Rios, and I'd like to welcome you to week 3 of GEO101 Physical Geography. This is sort of an update to a previous lesson, new material, slightly updated graphics. So having said all that, let's really get into the discussion. Again, if you have any questions that are administrative, always be sure to go to either the assistance module on Brightspace or contact me via email. That's available in the assistant or contact Professor Rios module on Brightspace. So let's get the lesson going. Again, we begin with the beginning here of the meteorological or atmospheric block. This covers composition and structure of the atmosphere and temperatures of the lower atmosphere. So let's get that going. Again, week 3, these are the lesson objectives, and I won't cover or read them all to you. You can sort of you can go over them rather on your own, but that is what the lesson objectives for this particular lesson happen to be. The atmosphere, think about it as an envelope that is remarkably thin, that wraps around the entire planet. It is mostly comprised of nitrogen and oxygen. So the majority of what you breathe every second of your life is nitrogen and oxygen, but there are lesser amounts of other gases. The greenhouse gases, which are key to weather and also life sustaining, would be, of course, CO2 and H2O, or water vapor. So think about the top here as a fresh air mixture. So you breathe in 78% nitrogen, only 21% oxygen, and then argon, neon, and so on, obviously in much smaller parts. And then the variable gases, from water vapor to carbon dioxide, monoxide, methane, ozone, and other parts. Now, these are available in small quantities, for example, CO2, but it is significant. And this number is already kind of dated. This number is already up to 424, and we'll go over that a little bit later. So these are the greenhouse gases. Condensation nuclei, which is nothing more than a tiny bit of dust and soot and smoke that help water vapor sort of coalesce around it to form things like water droplets. And then we'll talk about the idea of the upper atmosphere and what it contains. Mainly, in our case, ozone. So greenhouse is a natural but variable component of the atmosphere. It is found in the oceans, dissolved as carbonic acid, rather. It is expelled from volcanoes during eruptions, and it is also expelled by the decomposition of living material. It traps outgoing terrestrial energy, in other words, infrared energy, and that helps keep the planet warm. That is the greenhouse effect. And that is one of the key points in the homework. What is the greenhouse effect? And the greenhouse effect is nothing more than that blanket of gases which traps terrestrial energy, energy that is invisible to our eyes, and it's in the form of infrared radiation. Increasing amounts, of course, are linked to climate change. And this right here is, it'll be August, it reads August 12, 2024. And it is, so by the time you see this, it may be a little bit later than 2024. But the key here is that it is increasing at a rate of 2.3 parts per million per year. And when you see this sort of sawtooth pattern, the ups and downs and how predictable it is, it has to do with the northern hemisphere summer versus winter. So in the northern hemisphere, there are more trees. So during our winter, when the leaves are gone, there's more CO2 in the air because the trees aren't taking it out. And so it rises. And then spring comes along in summer, and all the leaves come out, and there's active photosynthesis going on, and CO2 drops. But notice how each high is higher than the previous high, and each low is higher than the previous low. So this is the actual record. It dates back to 1958. And this is actual real record. And it is gathered at Mauna Loa, with a little tiny exception in 2022 and 2021 when it was collected at Mauna Kea, very close by in Hawaii. And the reason you do it there is because Hawaii is a geographically isolated area of the world, and it's high up on a mountain, so you don't have artificial sources contaminating your reading. And that's why it's taken there. Another place on Earth where CO2 is recorded is what's called the Vostok ice cap in Antarctica. Obviously another isolated region. Water vapor. Water vapor is another variable, and it's actually highly variable component of the atmosphere. It is a greenhouse gas itself. Notice that, you have, when I say highly variable, I mean you could be in a desert, or you could be in the tropical jungles where it is very, very humid all the time. So it varies a lot with distance from the ocean, whether you're in the middle of a continent or adjacent to an ocean. It really, really depends. It is the only substance on Earth found in all three phases simultaneously. That's ice. So solid, liquid, and gas. And it is responsible for the absorption and the release of heat. This is called latent heat during phase changes. So whenever you go from water vapor to liquid, condensation, or when you go from liquid to gas, evaporation, there's either a release or a taking away of heat from the environment. And as a result, you either cool down or you warm up. Think about what happens when you are taking a hot shower in winter, but then you come out of the shower and you feel really, really cold. That's evaporation. That is taking heat away from the surface of your skin. And as a result, you feel colder. And so this is key to weather phenomena everywhere on Earth. Air pressure and density. So air density is the mass per unit volume, how much stuff is in a given space. Air pressure is the force per unit area. So imagine we all live at the bottom of the atmosphere. So the entire atmosphere is above us. Think of it as a column kind of directly over your head. And so that's air pressure. It's the weight or force exerted by that atmosphere above you. And the key here is that they both change very rapidly with increasing altitude. So here's an example. For example, if you're in the city of Mumbai, which is pretty close to sea level, or whether you are at the top of Mount Everest at 8,550 meters above sea level, by the time you get to the very, very top of Mount Everest, 70% of the atmosphere is below you, because the atmosphere is denser or thicker when you are close to the surface. And so, if you are a mountain climber, it is difficult to breathe at this elevation because there are so few air molecules around compared to sea level. Your body isn't used to dealing with that. The atmosphere is broken up into 4 layers. We are primarily going to focus on these 2. Again, each layer is characterized by a specific temperature rate, meaning how they change with height. And here's a really cool documentary. If you like documentaries, it's called The Edge of Space. It's a PBS special. Here's the link that you can go to. As of the last time I checked, this link still works. If it doesn't, let me know. But it is worth the watch if you do like documentaries. So here we are. We're going to look at the troposphere first. Then we're talking the stratosphere above that, and then there are other 2 layers that I'm not really going to get into that much. So the troposphere first. So this is where 95 to 99% of weather happens. The temperature generally decreases with height at that rate, roughly, the average, about 6.5 degrees Celsius per 1,000 meters. And it is very, very well mixed, meaning, and you see that in weather, right? Weather is a mixture of air. And sometimes the air goes up and it forms clouds. Sometimes it decreases and it sinks and dries up. So meaning well mixed here means there are rising and sinking currents happening all the time. There's a variable thickness from pole to equator, but it's on average around 11 kilometers. The stratosphere is separated by what's called a tropopause, which would be this little line. Think of it as a lid. And generally here, the temperature increases with height, which is a little bit different. And that increase is due to the absorption of ozone. And let me clarify that a bit. Energy absorption by ozone, that would be ultraviolet energy absorption by ozone. Then you have the mesosphere. By this point, 99% of the atmosphere is below you. You're not quite in space, but you're really close to it. And then the thermosphere, this is where you see things like the aurora borealis, the northern lights, those sort of beautiful dancing green, red, and pink streamers of light that you have to go far north into Canada and Greenland and Northern Europe to see. Again, this is characterized by a sharp increase in temperature with height. And that increase is due to there are so few oxygen atoms to absorb highly energetic energy that the temperatures just simply just rise up. But temperature here is a different, it's not like you could just take out a thermometer and just take a temperature. There's no way humans can exist here. You couldn't survive because the temperature really at this point doesn't really mean that much. You're essentially approaching space. If you go much further up, you're basically going to be in the region where you would find the International Space Station. Human-induced changes. Of course, there's climate change, ozone, and air pollution. So the ozone layer is a part of the planet that is important because it basically think of it as an umbrella. It literally shields humanity, people, living things, from a radiation that would otherwise cause lots of cancer. That would be ultraviolet radiation. So basically, we live down here. The ozone layer is in the stratosphere, and it protects us from ultraviolet radiation. So this ozone up here is good. Ozone in the lower atmosphere is bad. So again, the depletion of ozone layer, you have ultraviolet radiation. So how naturally it forms, you break up oxygen molecule, O2, into O and O. One of those combines with O2 and creates O3. That's ozone. Okay, now, when you naturally break it down, it does break down naturally using ultraviolet radiation, UVB and UVC. That naturally breaks it down into, again, O2 and O. So this would be the natural way of things happening. Unfortunately, because we have introduced compounds called chlorofluorocarbons, these are things that contain chlorine, fluorine, that introduction reacts with O3 and breaks it down unnaturally. And so what you end up having is a whole bunch of O2s and Os that interact with the Cl, the chlorine, creating other compounds. And as a result, you thin out that protective barrier. And so they started noticing it in the 1950s and 60s and 70s, but it is getting better. That is one environmental problem we have actually fixed. And I realize this graphic is old, but these are continuing to drop. And that's a good thing. That is absolutely a good thing, because a lot of these chemicals were banned in the 1990s. And so basically what's happening here is, if we had done no controls, if nothing had happened in the 1990s, ozone would have literally gone down to almost nothing, meaning you would have started to see by now an increase in the incidence of cancers, skin cancer primarily. But because we have, this future is not going to happen. And that's actually a good thing. We actually did make a concerted effort worldwide to do away with those chemicals. And as a result, ozone is beginning to sort of rebound. Again, the Montreal Protocol was adopted in 1987. And by the mid-1990s, everything had been either banned or people stopped using it. Air pollution. So there are types. So you can either have primary pollution. It's a direct entry into the atmosphere, like a fire that burns, say, plastic. And secondary, which would be the result of a subsequent chemical reaction, meaning something reacts with something else, causing a third something, and that it would be considered secondary pollution. Okay. And so the idea of, primary nitrogen oxides, sulfur dioxide, for example, carbon monoxide, these are all primary types of pollution. Air pollution, for example, would be a secondary type. So smog, which is smoke and fog combined. So now you're mixing whatever chemicals are out there with smoke. And that smoke could come from factories, from jetliners, from cars, whatever the case might be. And that is a secondary type of pollution because it is a result of a chemical reaction. So there are cities in the world like Mumbai, like Santiago in Chile, like Mexico City, Los Angeles to a lesser extent than it used to be, where it happens quite a bit. And geography tends to help support that. All right, difference between weather and climate. So weather is highly changeable, and they're highly changeable measurement of any of these. What's it going to be like today? What's the forecast for the weekend? Is it going to rain? How much snow are we going to get? Is it going to be cloudy? Can I go to the football game? Can I have that picnic outside? That's weather. And here's a weather map showing you fronts where you're going to have rain, thunderstorms, where there's a high critical fire threat, those kinds of things. Now, whether, what is climate, on the other hand? Climate is a measure of weather, and the key here is averaged over time. Generally, decades. The more data you have, the better. Ideally, 30 years. And then when you do this average over time, you begin to see seasonal patterns emerge. So the day-to-day weather extremes are smoothed out. So think about it, pick a date, pick July 4th. So let's say the average temperature in July 4 is 81. I'm making that up, but let's just say it's 81. Well, maybe what was it like in 2020, 2019, 2015, 2010, 2005, 1995, 1985. And you can take every single July 4th temperature, add them up, divide by the number of years, and there's your average. Now, if you can go back July 4 all the way to the year 1900, wow, now you have a whole bunch of years. That's a better record than if you just went back to, say, 1990. So the more data you have, the better. It smooths out all the little extremes. Because let's say in year 1, the temperature was 81. Oh, wow, that's exactly the average. But the year before that, it was 103. Wow, that's really hot. And the year before that, it was 70. Well, that's much cooler. So you take all those extremes and you sort of even them out. That's climate. That's what climate tells you. Controls of climate. So one of the bigger ones are ocean currents. And ocean currents can be warm, like the Gulf Stream, or the Kuroshio current near Japan. And ocean currents can be cold, like the Labrador current, or the California current, or the Humboldt current near Peru. So they're cold because they're coming from subpolar regions, and they're hot because they're coming from equatorial regions. Pretty straightforward. But currents can influence the type of climate you experience in a particular region. So if you're near a hot ocean current or a warm current, you tend to experience more humid weather with more thunderstorms and rain than if you are adjacent to a cold current. And here's the idea of warm, ocean temperatures. So this color here is about 30 to 32 degrees Celsius water. So the Gulf of Mexico is, and that would be roughly between 88 and 90 degrees. So obviously very, very warm. Notice this ribbon. This is called the Gulf Stream. But notice if you're near Maine, the water temperatures there are still relatively chilly in the 40s and 50s still. And this was taken in August. And this could be August 2020, 2015, 2010, so on and so forth. Just because it happens to be this particular year doesn't necessarily mean that they're going to be that much different from year to year. Here's another one. This happens to be a January 2024 image. So this is our winter. Notice how the temperatures off our shore are in this sort of green color, which would be roughly in the 40s and 50s. Okay. Notice that at the equator, it's pretty warm, even though it is January. So, and notice even in the Gulf of Mexico, you see this little blue. So that would be roughly somewhere in the 70s. Now, fast forward to August, and notice how that changed. So let me go back to winter, summer, winter, summer. Now in summer, this happens to be August. The entire Gulf of Mexico is easily in the 80s. Parts of the Pacific Ocean are 80s to 90 or higher. If you go to the Persian Gulf. The Persian Gulf can be anywhere between 95 and 98 degrees. That's hot water. So notice the difference in winter in the Persian Gulf. Still warm, but it's really in the 70s versus August. Look at the Red Sea. Oh, there you go. So big difference. Anywhere where you see white, that's ice, sea ice. So notice how the sea ice disappears for the most part. And notice how it changes in the southern hemisphere. So in August, it is winter down here. So notice how much more expensive the ice sheet is versus their summer, January. Other climate controls, topographic barriers, that would be mountains, mountain chains. So if you have a mountain with a prevailing wind direction, you tend to have a green area next to a very dry area. So another control would be land-water contrasts. So the ocean heats up fast, but it also cools off fast. I'm sorry, land heats up fast, but cools off fast. Water heats up slowly, but it cools off slowly. So this maritime versus continental effect means something. So here's an example. So let's look at the city of Omaha, Nebraska, San Francisco. They are both roughly around, similar latitudes, but Omaha gets much hotter in summer, but much colder in winter. San Francisco doesn't really have hot summers, and their winters aren't especially cold. Here's a city in Siberia, Verkhoyansk in Russia, way up north, far from the ocean. They get pretty warm in summer, but exceptionally cold in winter. That is the land, water, or the continental maritime effect. Again, July versus January temperatures. And then, of course, altitude makes a big difference. So this is the mountain called K2. That would be the letter K followed by the number 2. It's in Pakistan, near its border with China. It is the second tallest mountain on Earth. And as you can see, altitude makes a big difference. It is permanently encased in ice. So even up here, climate change doesn't really mean that much. It's cold. It's cold all the time. So these are like glaciers that have been here for, millennia. But altitude matters. So remember, in the lower part of the atmosphere, temperature decreases with height. So you may notice this if you travel out west to places like New Mexico, Arizona, Colorado, Wyoming, where you can travel a very short distance. And by that, I mean the distance between Middletown and Port Jervis. And because the altitude changes so much, you can go from desert to pine forest. We don't really see that much in New York because the climate doesn't really change that much from region to region, but out west it does. And if you've traveled out west, you know what I'm talking about. So you can go from grasslands to scrub to forest to subalpine forest to tundra in a very short horizontal distance as you go up in elevation. Temperature, what is it? We Americans, basically we are about the only ones that use the Fahrenheit scale. I like it. I prefer the Fahrenheit scale as much as I like metric. I think Fahrenheit is a better temperature scale, but the rest of the world basically sticks to Celsius. And then there's, of course, kelvins. And the good thing about Kelvin is it has no negative numbers. So that's about, So it's good for math because there's no negative numbers to worry about. In any event, these are the three temperature scales, and basically it's a measure of molecular activity. So the hotter something is, the more those sort of molecules within that substance are vibrating. Temperature and stability. So stability or instability is related to, from a weather point of view, thunderstorms or fog, depending on the type of stability you're dealing with. So a lapse rate sounds complicated, but it's not. A temperature lapse rate, it's nothing more than how temperature changes with height. So again, in the lower part of the atmosphere, we talked about how temperature typically decreases with height. And so the math symbol uses negative. So -3 degrees per whatever. Get it? It's telling you that as you go up, the temperature is going down. Now, in some cases, the temperature increases with height, and you would use a positive symbol. That's it. So notice that in the lower atmosphere, you're going from about an average of about 15, 16. So by the time you get to around, oh, I don't know, what is that, 16 kilometers? Oh, the temperature is like, wow, -60 something. Get it? It is decreasing with height. And then you get these things called environmental lapse rates. So you have the adiabatic lapse rate, which is dry. So the dry version of it is -10 degrees Celsius per 1,000 meters. Oh. And then the saturated version of it is -5 to 6 per 1,000 meters. Okay, so we'll get more into that coming up. Stability. When something is stable, think of fog in the morning, right? Fog seems serene, seems flat. It doesn't seem like it's turbulent in any way. That's stability. That usually means cold air is at the bottom, warm air is at the top. Right? Does that make sense? Stable. Cold air is heavy. It sinks, so it's at the bottom. Warm air rises. So that makes sense. That's stable. Unstable is sort of the opposite. So think about a bubbly summer afternoon when you see all these big sort of popcorn looking clouds. That is generally unstable air. So we'll get into that. So now, what is an adiabatic process? This complicated sounding term. And so basically it's all it is the heating or cooling that takes place as pressure changes. So now, pressure is, the symbol means proportional to temperature. So as the pressure goes down, meaning as you go up in elevation, your temperature decreases. And you all kind of know this. That's why you see snow on mountaintops and you don't see snow in the valleys, generally speaking. And you'll see this in New York, close to where we are. If you ever go to West Point, sometimes there'll be snow up on 9W on that high point that overlooks West Point. You'll see snow up there, but when you go down to the school itself, there's no snow on the ground. So that's a very local sort of example of this. So imagine imagine the bottom of this page being where you are. You're standing here, okay? The relative humidity is less than 100%, meaning the air is unsaturated. There's no fog, there's no rain. So you're below what's referred to as the LCL, the lifting condensation level. That's the point that you have to lift air to actually be able to see a cloud. So at this point, as that air rises from down here all the way up to here, the air is going to decrease in temperature at 10 degrees per 1,000 meters. Okay? Now you get, at this point, the temperature of the air and the dew point are the same. Suddenly, you have a relative humidity of 100%. You get cloud forming. This is the lifting condensation level, the level to which you have to lift air to get condensation. Let the term itself help define it for you. Now the humidity is 100%, and above this, the air continues to cool, but it cools at a lesser rate because condensation releases heat, which brings that number from 10 to 6. Imagine it's like having the air conditioning in your car going full blast, but you've left your window open just a little bit, so it lets in a little bit of warm air, so it doesn't cool down as fast as it would otherwise would. Okay, that's my sort of visual to sort of get around that idea. If you've ever noticed, you look at clouds on a day when there's lots of clouds in the air, and they all seem to have the same base, right? It's like somebody took a knife and just cut right through a certain point. That's the lifting condensation level. All that air had to be lifted to a certain level before condensation took place. Okay. In desert regions, this level is much higher. Las Vegas, Phoenix. Now, in very warm, wet places like Miami, Atlanta, New Orleans, that level is much lower. And here's from your book. Again, you have, this happens to be the Cascade Range of Oregon. Here we're looking north. You looking at this image are south. You're looking north into the image. So to the right is east and to the left is west. Make sense? You're bringing in moist air from the Pacific. It is colliding with the mountain. It rains and snows, and this side of the mountain is green or snow covered. But then the air now goes on the other side and it's now descending and it is drying. And this area is full of deserts. So that's at that same level, the temperature was 59 degrees Fahrenheit, but at this other side, it's 74. Because not only did you leave all the moisture on this side, but you carry the heat along with it. So it ends up being that this side is drier and warmer. This side is cooler and wetter. That is topographic or orographic lifting of the air. And here's a great example in the United States, Washington and Oregon. Everybody thinks of Washington, Seattle, they think it's always raining, raining, raining. And it does, and it rains a lot. And it rains a lot in Portland and in Salem and in Eugene and so on. But if you go to the east side of Washington or the east side of Oregon, it is exceptionally dry. Why? Because you have this Cascade Range, and all the moisture falls on the windward side, and the leeward side is high and dry. And then here's, again, I'll go through this pretty quickly here. This is my less fancy graphic. Wind direction, lifting condensation level happens, clouds form, it may rain, it may snow, depending on the year, time of year rather. Air continues to expand and cool at a lesser rate, but the reason why is latent heat being released. And now it cools at a lesser rate, and eventually it goes down the hill and it descends and it compresses and it warms. Think about compression. Imagine, don't do this, but imagine you take your hand and you rub it up against your desk for a while, right? All that friction, all that compression. Suddenly, if you don't watch it, you're going to burn your hand because you're generating heat. That's essentially what's happening in a much larger scale on the leeward side of the mountain. There you go. Stability is the ability to come back from, so for example, if the air is stable and you push it, it comes right back to where it was. But if it's unstable and you push it, sort of a new reality takes place. And this is sort of like an interesting example. I mean, they're using here this sort of like triangular wedge, right? If you push on this, it'll just sort of bounce for a little bit and go right back to where it was. That's stable. Whereas if you sort of put on its point and you push in either direction, it's going to fall. Unstable. Well, from a weather perspective, this would mean weather, thunderstorms, rainfall, snow. And from a stable point of view, it means not much change. So think of stability as no change and instability as change in the weather from that perspective. Different rates. Let's get into, when the atmosphere is unstable. So look at that image right there. You can literally see the instability, right? It's bubbling up. Notice how you have these sort of towers. You have this very distinctive anvil. You have these sort of popcorn looking bubbles of convection. This is unstable air. If you happen to be under all of this, you're probably getting thunder and lightning and heavy rain, maybe strong winds. Stability, on the other hand, can lead to pollution issues. So because the air temperature increases with height, it literally forms like a lid, a temperature lid, which traps all the air near the ground. And if that air happens to be dirty, then you get events like what happened in Beijing, in China, Mexico City, Los Angeles. Lots of industry, lots of cars. And if you have a stable atmosphere, everything just sort of gets trapped. And you've seen that. It becomes really obvious. Here's an example of stability and pollution. Notice how everything looks very flat. There's no definition to this cloud. Or right here. Notice how, in this case, everything is trapped at the valley floor. So everything is down there. And, once you cross over here, suddenly you're in the clear. And that's the lesson. That's it for today. And, we'll get more into versions of stability and instability in other lessons, specifically when we talk about air pressure and winds and circulation patterns. But this at least gets you started thinking about the idea of convection, stability, instability, and temperature of the lower atmosphere. If you have any questions, please let me know. Otherwise, have a great rest of your semester, and we'll talk to you soon. Bye.